Shortly we're going to have the board candidate panel come up here. But before we do, we're going to let the runners-up of the hackathon give you an overview of their work. And the first team that's going to come up is the Kofefe Kafka. I'm having to practice that name, so thank you.
Oh, click it. Okay. Hello. I will not try to pronounce our name for team. And let's talk about our solution. So it's egress traffic controller architecture. We were trying to regress regular controller with Kafka messaging bus. And we set up in a Google Cloud infrastructure our environment. It was one iOS XRV router and few Linux Quagga instances just to reduce the memory footprint. And we start to tickle around. So my colleague Nick will talk about it in a moment.
So hi everyone. So when we look at the kind of the goals for the hackathon, basically was to collect data from the network. So we had a network running BGP, do something with the data, apply some business logic, and then inject some changes into the network. So for that purpose, we set up like a microservices architecture. So we try to kind of set different microservices. So each one of the members of this team could write on their own programming language. So the first step was to collect data. So what we did was basically to subscribe to a telemetry stream using OpenConfig. So we will get the data, and we will have a processing engine that will basically do some parsing and then create a new message with some counters that will be interested for someone else. In this case, we will just publish back to a Kafka bus, let's say the data rates, and interface counters. So we kind of agreed on the message. It was just a JSON file with those counters, so it was a much simpler message. And then we will have someone, another microservice, applying the business rules, basically looking for like a given number or threshold that was crossed, so it can then create an alarm, which was another message pushed back to the Kafka bus. And then we will then have another microservice that was listening to this specific topic that then will trigger changes based on the nature of this event. In this case, we wanted to not only use the Cisco Service Layer API to inject or program the FEV on the router, but also do it through GoBGP. So you can either use either one of those methods to program the routing table. So I'll hand it off.
Yep. So our structure was quite layered. And at the bottom layer, we have our services. And all our services communicating to Kafka. The beauty of this approach that any type of data can be published, and we just use telemetry one. To trigger all the actions, we separate and abstract our business logic. It was YAML-based files. We can call them rules. And based on the current rules, we can try some actions. And for example, if we jitter thresholds some value, we just reprogram the route. To reprogram the route or to update it, we use Service Layer API. It's iOS XR API to program your RIB, and not only RIB. And my colleague Akshat Sharma will be covering full session on Wednesday, so go, you can check it in details later this week. And let's talk more about benefits for this solution. As I said previously, any type of data could be published to a message bus. So we don't care if it's telemetry, SNP, or just syslog messages. We can post whatever we want to Kafka bus. Our logic doesn't depend on the other layers, and we use the format which we wanted. In our case, it was YAML. We can easily replace it to JSON format. We can do some API for that, and we are not limited to any solution, so we can easily replace it. And publishing subscribe mechanism, it's one of the typical one, which is language agnostic. So Some of the hacks which we did was in Golang. Some pieces are in Python, and we are language agnostic in this case. Yep. So thanks for attention. If you have any question for us, you can find us in the lobby at any time.
No, that's fine. Basically, the code is available on that GitHub repo. The technologies we use, as he said, basically is Golang, Python, gRPC, OpenConfig, and the service layer API, aside from Go BGP. So if anyone is interested, just take a look at the GitHub repo, or just come and talk to us. That's it.
Thank you.
Thank you, Kofefe Kafka. And I'm going to invite the other team, Hack Overflow.
Good afternoon, everyone. We are graduate students from the University of Colorado Boulder. My name is Rishikesh, his Pratik, Ashutosh, and Tanvi. We are a mixture of network security and network engineering. So yesterday, during the hackathon, what we did was a trial version of self-healing networks. So what basically we did was, in a scenario where you have multiple ISPs, you would want to achieve redundancy. For example, if you could see the diagram over there, that's a draft model we made before starting the hackathon. You could see 3 ISPs over there, where ISP1 is the main ISP, and then you have ISP2 and ISP3. But there is just a single path which is talking between the ISPs. And you have a redundancy path, like at a single point of time, either ISP1 is connected to ISP2 or ISP1 is connected to ISP3. In order to achieve this, we've selected an open approach where we used controllers, and we've also used a model of router, which is a Quagga router. We've used Quagga because it's easy to configure, and at the same time, it's easy to automate. So in a single ISP, the model we used was the ISP would have a RU controller, and then it would have a mininet topology. Instead of using a live topology model, we've used mininet in order to simulate a topology, which would be an open virtual switch and then host. You can see that the RU is connected to the Quagga routers, and the Quagga is connected to the other Quagga in the next internet service provider. So what we did was we ran iBGP within the Quagga and the controller, and then we've run external BGP between the different Quaggas of the different ISPs. So you might wonder what's different between this and what is happening in the real world. The major thing we tried to achieve in the 6 hours of duration during the hackathon was we tried to automate a redundant scenario. And how would it be self-healing? We have a Python script. We have a Python script which would actually poll the different Quagga routers to see the packet loss and the RTT. And depending upon the values, it will select the best path. So my team member would go with the rest of the presentation.
So the intention was not to reinvent the wheel. So something like this you might have seen where you do a polling of the particular prefix, and then you might change the local preference for the BGP route. But what we tried to achieve was that what we wanted, so we have had a RU topology, which is like an actual SDN topology using OpenFlow protocol, and that's what we were trying to configure. So what the script does is it will continuously poll the prefixes, get round trip time or some sort of latency. So it will have a particular threshold value. So if the threshold exceeds a particular value, then the route is directly changed, which we are for using the Python script, where the local preference is directly changed. So as you can see in the last diagram, there are like 2 paths for the same prefix, but one path is chosen over the other because it has a lower latency. So this is the Quagga of the ISP2 and Quagga of the ISP3. So there also we can see that for a particular prefix, due to the change in latency, we are changing the routes. Also, we didn't want to ignore security, so we had a prototype of Snort IDS. So what it does is basically we have the edge router, Quagga router, and if an unrecognized peer is trying to establish neighborship on port 179 or any type of malicious traffic is trying to reach on the edge router, that can be like directly mapped and tracked via the Snort IDS. And the Snort talks via REST API to the Ryu controller. So that will automatically dynamically apply ACL rules to the edge router to directly block them. And we will also have, like, we also had an email notification system. So any change in the local preference for any type of malicious activity, we directly get email notification to the operator. So what the intention was that we can have a prototype of Snort changing the preference for routing where the SDN topology exists. So migration from a traditional to a hybrid network is possible, and that's what we wanted to demonstrate. And along with it, we also had the plan of having a GUI where the operations team can continuously see how is the congestion in a particular network, generate database reports. So basically having an audit trail. So that's what we tried to do. I'll hand over the mic to Rishi.
So this is the current perspective of our prototype. In the future, what we were planning was we would have a load balancing scenario where instead of using just a single link in order to connect to an ISP, we would have multiple links connecting the ISPs. So one route would be a primary route for this particular ISP. Let's say we're connecting India and Germany. One route would just go for India, and the other route would just go for Germany. At the same time, the other route would be the backup for the primary route. So instead of using just one route and just disabling the other route, that's a future scenario where we are thinking of implementing a load balancing effort. And right now, due to time constraint, we have not automated the configuration generation. So we just manually created 2 different BGP configurations and used them. But in the future, we are planning to do the automation configuration using Jinja 2 templates and Ansible. And we will be doing it in the next coming months. So thank you so much for the opportunity. We got a great opportunity to learn during this hackathon. Thank you so much.